In the last class, we talked about circle segment theorems pertaining to intersecting chords. And we referred to the four parts that were created by the intersecting chords as our A and our B and our C and our D. I'm using lowercase letters because these represent segments. And we learned quite simply that A times B will always be equal to C times D. Pretty simple theorem there. And now we're going to move on to two different types of problems. One that involves two secants to the same circle, and then another one that involves a tangent and a secant to the same circle. So just to get us started, I drew in these red lines that aren't really there in a problem, but I draw that line to refer to the whole secant segment from its starting point to its end point. And today we're going to refer to that whole secant length as our A. And even though there are two parts of it that we can refer to, the part that's inside the circle, the interior, and the part that's outside, the exterior, we're going to be most interested in the exterior part, which we're going to call our B. Then we go to the other secant, and we're going to refer to its entire length, the red segment here, as our C, and its interior or exterior part rather as the D. And what we're going to see very soon is that again, A times B is equal to C times D. We'll see that a little bit more on the next page. And then we're going to finish this lesson with a tangent secant problem. We're going to have the whole entire tangent from its starting point to its end point on the circle as our A. There's only one part there. Then we get to the secant, and we're going to think of the secant just like these. There's the whole. We'll call this, in this case, our B. And then we're going to call the exterior part our C. And then we're going to learn in a short little while that the whole times the exterior part, well, that's the same part in the tangent. So that's going to be A times A, which is A squared, is equal to the whole times its exterior part. But we're going to get into these a little bit more right now. So let's look at the first theorem. If two secant segments are drawn to a circle from the same external point, the product of the length of one secant segment and its external part is equal to the product of the length of the other secant segment and its external part. Sometimes we write the secant formula as it's the whole of one times its external part is equal to the other whole times its external part. And if you label, as they did right here, the same way that I labeled mine on the previous page, that the A is the whole secant, the B is its exterior part, and then the C is the whole other secant, and the D is its exterior part, then quite simply, A times B is equal to C times D. Let's take a look at some examples. I have this here actually before we get to the examples. I'm not going to hold you responsible this year, 2020, for this proof. But for those of you who are interested in the proof of this particular theorem, here it is. You could pause your screen, take a look at it, copy it, take a picture of it, and feel free to ask me any questions about it in any time in class, online, or through email. I'll be more than happy to talk about it. Okay, here's example number 1. Question 19. In the diagram below, PAB and PCD are secants to the same circle. If PA is 4, okay, I'm going to put in some of these numbers as we go along here. If PA is 4 and AB is 5 and PD, now whenever they refer to a whole entire secant, I like to draw that line here, and PD is the whole entire secant. So that entire secant is 12. What is PC? Now, if the question that they're asking is one of the parts that's included in the theorem, I will mark it as X if we don't have an X yet. And as we saw earlier, while it's important to know that this part of the secant is 4 and that the interior part is 5, more important to the theorem is the whole. And of course, if they tell us that this is 4 units long and that this is 5 units long, we can easily add that up and know that the whole secant is 9 units long. 4 plus 5 is 9. And now we're ready to put together an equation. But since this is the first one, let's not forget that it's the whole of 1 times its exterior part will be equal to the whole of the other times its exterior part, right? Whole 1 times its exterior part 1 times the whole 2 times its exterior part 2. And if you remember the way that we labeled it with A, B, C, and D, it's quite simple. A, the whole, times its exterior part, B, is equal to the other whole, C, times its exterior part, which is D. So now all we got to do is substitute. So let's start with this one up here. Here we have the whole, which is 9, times its exterior part, which is 4, will be equal to the whole C of the other, which is 12, times its exterior part, which is what we're looking for, which is our X. So quite simply, 36 is equal to 12X. Divide both sides by 12. We get 3 is equal to X, which is the same as saying X is equal to 3. The X is representing PC. That is what the question is. PC is equal to 3. Question number 20. In the diagram below, secant segments PR and PT intersect at P. If PR is 10, all right, there they're giving me a hole, so I like to do that right there. If PR is 10 and PQ is 6 and PS is 5, find PT. Well, PT happens to be the whole secant here, which is a part of my theorem. So I will represent that here as my X. And now I'm just going to remember that the whole of 1 times its exterior part is equal to the whole of the other times its exterior part. If I remember where my A, B, C, and D's are here, quite simply, we're going to have the whole times the exterior is equal to the whole times the exterior. And if we put that together, we get 60 is equal to X times 5, which of course I prefer to write as 5X. Divide by 5. 12 is equal to my X, or X is equal to 12. X represents PT. PT is the question here. So quite simply, PT is equal to 12. All right, let's move on to the secant tangent theorem or formula. If a secant segment and tangent segment are drawn to a circle from the same external point, the length of the tangent segment is the geometric mean between the length of the secant segment and the length of the external part of the secant segment. So what this is really saying by geometric mean, the last time we saw that question or that word was when we talked about the leg rule and the altitude rule, because when we did the leg rule, the leg multiplied with itself, meaning it was a mean proportion, or the in the altitude in the leg rule, the leg multiplied to itself. So here, what they're saying is that when we see a tangent, you could think of the tangent whole and the tangent exterior part being the same exact part because it only touches the circle at one point. So therefore, it's the tangent times itself, which is the tangent squared, right? So here, if we label this the way I labeled mine earlier, as the tangent as being the A, the whole other secant being the B, and the exterior part being the C, it's really the same as what we've been doing. It's the whole times the exterior part is equal to the tangent times itself, which is the tangent squared. So you could see that it comes out a little different in its look, but it's really the same thing, right? The tangent squared is equal to the whole secant times its exterior part. Let's look at some examples. Again, there is a proof for this theorem. You might notice that these proofs all are creations of triangles that turn out to be similar. And then you have the corresponding sides of similar triangles are in proportion, which leads to the product of the means is equal to the product of the extremes, which all these formulas are derived from. Again, this is optional, but anyone who wants to discuss this in the future, I am more than open to doing that with you. Okay, here's an example. Number 15. In the accompanying diagram, AP is a tangent and PBC is a secant to circle O. All right, well, let's put in some information here. If PC, well, I see that PC is the whole secant. So again, I'm going to draw one of these lines and put in the number, which is 12. And BC is 9. Find the length of AP. Now I notice that AP happens to be the tangent. I know that's part of the theorem, so I'm going to put an X there happily. And, oh, it's not degrees, sorry, it's just X. And however, when I look at the secant, they've given me the whole, but instead of giving me the exterior, they've given me the interior. Okay, well, the interior part of the secant is not a part of the theorem or formula. However, it does enable me to figure out the exterior part, because if the whole thing is 12 feet long and the interior part is 9 feet, quite simply, 12 minus 9 is 3. So now I have all the parts that I need. And here we're remembering that the tangent, I'm just going to put TAN, squared will be equal to the secant times its exterior part. Well, let's substitute the A, B's, and the C's. That means my A, which is my tangent, squared, is equal to the whole secant, which is my B, times the exterior part, which is C. All right, let's substitute now. The tangent, which is my X, squared will be equal to the whole secant, which is 12, times its exterior part, which is 3. So quite simply, we end up with a square number, which makes this problem square root, quite simple. X is equal to 6. That's what they were asking for because AP is represented by my X. So AP is equal to 6 is the final answer. 16. In the accompanying diagram, TS is tangent to circle O at S, and TUV is a secant. If TU is 3 and UV is 9, find the length of TS. Well, this is not that different than the last question. However, it's just demonstrating that here we are given the exterior and the interior, and we know that we need the whole and the exterior. Well, if this is 3 feet and this is 9 feet, 3 plus 9 would make the entire secant 12 feet long. And now we're ready just to substitute into our A squared is equal to BC, remembering that A is the whole tangent and that B is the exterior part of the whole secant rather, and the C is the exterior part. So here we have x squared is equal to the whole, which is 12, times the exterior part. This is the same as the other previous problem, as you now see. Square root x is equal to 6. TS is what they were asking for. TS is my x, is equal to 6. And our last problem of this video lesson, in the accompanying diagram, PC is tangent to circle O at C. PAB is a secant. If PC is 8, in this problem they put it there for me, and PA is 4, they put that in for me, find AB. So here's a problem where there's several different ways we can go about it. So I'm actually going to do this problem 2 times. Well, one way to do this problem that I like is to not put an x at AB, because AB is the interior part and it's not a part of my formula. So if I do put an x there, I'm going to have to represent the whole entire secant as x plus 4. Then I'm getting involved with binomials. I have to remember to distribute and so on and so forth. So what I'm going to do instead is represent the whole secant as x, and then make a little bit of an adjustment at the end of this problem. Because now I could say that my tangent squared is equal to my whole times my exterior part. My tangent squared is equal to the whole times its exterior part. My tangent squared is 64 is equal to 4x. Divide by 4, and you get x is equal to 16. Now, the only thing that's probably a little bit more complicated about my decision to make x equal to the whole secant is now that you have to remember that this is what we were looking for, AB. And now that I have x equal to 16, I now have to make one final calculation in order to find out AB. I got to take the 16 and subtract 4, which is equal to 12. So I have to write AB is equal to 12. So that's the only tricky part there. However, let me show you this problem in a slightly different manner that some of you might choose to do. So I'm going to erase this and start fresh with a different approach. The next approach is going to stick with the idea that we always make x what we're looking for, which I know a lot of you automatically do. It's not a bad thing. As a teacher, I probably said it many times, make x what you're looking for. And if we did in that case, we would say, oh, find AB. I would say, oh, AB is my x. But then you have to realize that that x is not a part of your theorem, and the whole secant is. And then the representation of the whole secant will be your x plus your 4, right? Your x plus your 4, because it's this part plus this part would make the whole. And now when we put this together in our a squared is equal to the whole times the exterior part, we have to remember that 8 squared is going to be equal to the whole here, which is x plus 4. And because it's a binomial, I'm going to put that in parentheses for sure and put the 4 in front of it rather than after it. So I remember to distribute that when we multiply. And I'm going to get 64 is equal to 4x plus 16. And then we're going to get 64 minus 16 is equal to 4x, which is going to be 48 is equal to 4x. Divide both sides by 4, you can get 12 is equal to x, or x is equal to 12. However, this is probably the benefit of this particular problem, is that at the very end, when we have x is equal to 12, x is what we were looking for, and we got our answer right away. AB is equal to 12. Whichever your approach, we still get the correct answer if we do everything right. So I believe that's all for today. I hope you found this video useful, and if you did, please subscribe to Mr. Frank's YouTube channel. See you soon.